The incredible scale of the universe, from the Big Bang to today. The universe was born with the Big Bang as an unimaginably hot, dense point. When the universe was just 10 to 34 of a second or so old, hundredth of a billionth of a trillionth of a trillionth of a second in age, it experienced an incredible burst of expansion known as inflation, in which space itself expanded faster than the speed of light. During this period, the universe doubled in size at least 90 times, going from subatomic size to golf ball sized almost instantaneously. The work that goes into understanding the expanding universe comes from a combination of theoretical physics and direct observations by astronomers. However, in some cases astronomers have not been able to see direct evidence, such as the case of gravitational waves associated with the cosmic microwave background, the leftover radiation from the Big Bang. A preliminary announcement about finding these waves in 2014 was quickly retracted, after astronomers found the signal detected could be explained by dust in the Milky Way. According to NASA, after inflation the growth of the universe continued, but at a slower rate. As space expanded, the universe cooled and matter formed. 1 second after the Big Bang, the universe was filled with neutrons, protons, electrons, anti-electrons, photons and neutrinos. During the first 3 minutes of the universe, the light elements were born during a process known as Big Bang nucleosynthesis. Temperatures cooled from 100 nonillion, 1032, Kelvin to 1 billion, 109, Kelvin, and protons and neutrons collided to make deuterium, an isotope of hydrogen. Most of the deuterium combined to make helium, and trace amounts of lithium were also generated. For the first 380,000 years or so, the universe was essentially too hot for light to shine, according to France's National Center of Space Research, Centre National d'études spatiales, or CNES. The heat of creation smashed atoms together with enough force to break them up into a dense plasma, an opaque soup of protons, neutrons and electrons that scattered light like fog. Roughly 380,000 years after the Big Bang, matter cooled enough for atoms to form during the era of recombination, resulting in a transparent, electrically neutral gas, according to NASA. This set loose the initial flash of light created during the Big Bang, which is detectable today as cosmic microwave background radiation. However, after this point, the universe was plunged into darkness, since no stars or any other bright objects had formed yet. About 400 million years after the Big Bang, the universe began to emerge from the cosmic dark ages during the epoch of reionization. During this time, which lasted more than 500 million years, clumps of gas collapsed enough to form the first stars and galaxies, whose energetic ultraviolet light ionized and destroyed most of the neutral hydrogen. Although the expansion of the universe gradually slowed down as the matter in the universe pulled on itself via gravity, about 5 or 6 billion years after the Big Bang, according to the universe did not expand into space, as space did not exist before the universe, according to NASA. Instead, it is better to think of the Big Bang as the simultaneous appearance of space everywhere in the universe. The universe has not expanded from any one spot since the Big Bang, rather, space itself has been stretching and carrying matter with it. Since the universe by its definition encompasses all of space and time as we know it, NASA says it is beyond the model of the Big Bang, opens a new tab, to say what the universe is expanding into or what gave rise to the Big Bang. Although there are models that speculate about these questions, none of them have made realistically testable predictions as of yet. In 2014, scientists from the Harvard-Smithsonian Center for Astrophysics announced that they had found a faint signal in the cosmic microwave background that could be the first direct evidence of gravitational waves themselves. Considered a smoking gun for the Big Bang, the findings were hotly debated, and astronomers soon retracted their results when they realized dust in the Milky Way could explain their findings. The universe is currently estimated at roughly 13.8 billion years old, give or take 130 million years. In comparison, the solar system is only about 4.6 billion years old. This estimate came from measuring the composition of matter and energy density in the universe. This allowed researchers to compute how fast the universe expanded in the past. With that knowledge, they could turn the clock back and extrapolate when the Big Bang happened. The time between then and now is the age of the universe. Scientists think that in the earliest moments of the universe, there was no structure to it to speak of, with matter and energy distributed nearly uniformly throughout. According to NASA, opens a new tab, The gravitational pull of small fluctuations in the density of matter back then gave rise to the vast web-like structure of stars and emptiness seen today. Dense regions pulled in more and more matter through gravity, and the more massive they became, the more matter they could pull in through gravity, forming stars, galaxies, and larger structures known as clusters, superclusters. Less dense regions did not grow, evolving into area of seemingly empty space called voids. Until a few decades ago, astronomers thought that the universe was composed almost entirely of ordinary atoms, or baryonic matter, according to NASA. However, recently there has been ever more evidence that suggests most of the ingredients making up the universe come in forms that we cannot see. When it comes to the atoms we are familiar with, hydrogen makes up about 75%, while helium makes up about 25%, with heavier elements making up only a tiny fraction of the universe's atoms, according to NASA. The shape of the universe and whether or not it is finite or infinite in extent depends on the struggle between the rate of its expansion and the pull of gravity. The strength of the pull in question depends in part on the density of the matter in the universe. If the density of the universe exceeds a specific critical value, then the universe is positive curved, like the surface of a sphere. This means light beams that are initially parallel will converge slowly, eventually cross and return back to their starting point, if the universe lasts long enough. If so, according to NASA, the universe is not infinite but has no end, just as the area on the surface of a sphere is not infinite but has no beginning or end to speak of. The universe will eventually stop expanding and start collapsing in on itself, the so-called Big Crunch. If the density of the universe is less than this critical density, then the geometry of space is negatively curved, like the surface of a saddle. If so, the universe has no bounds and will expand forever. If the density of the universe exactly equals the critical density, then the geometry of the universe is flat, with zero curvature like a sheet of paper, according to NASA. If so, the universe has no bounds and will expand forever, but the rate of expansion will gradually approach zero, opens in new tab, after an infinite amount of time. Recent measurements suggest that the universe is flat with only a 0.4% margin of error, according to NASA. Like, comment, share and subscribe to my channel.